Okay, so I'm going to move on to our next divide and conquer searching algorithm, which is Quicksort. This is actually the algorithm that's used the most in reality, and it's the one that most programming languages have as their built-in sorting method. So Quicksort is quite similar to merge sort, however things are really done in the opposite direction. It's also divide and conquer, and it's usually implemented recursively. Well, actually, I'll be honest, by students, when you first learn it, you usually think of it as a recursive algorithm and you implement it that way. If you look at the actual implementation of something like C++ or Java, I bet you it's not recursive. I know it's not in C++ because it's not a particularly efficient way to implement it. And sorting is done so often that people really try to find the most efficient ways to operate. The main idea behind Quicksort is to divide the array into two parts based on a comparison with what's called a pivot element. That is whether an element is greater than or equal to or less than the pivot. Then divide the subarrays in the same way, and then they can be concatenated together into a sorted array. So let's see an example as algorithm in practice. Oh, actually, no, we're going to describe it first. Okay. I did make these slides, but sometimes you forget what order they're in. So what we do is select a pivot element from the array. It could be any element in the array. We create three sub-arrays, one which is less than the pivot, one which is equal to the pivot, and one that's greater than the pivot. Elements that are less than the pivot got put in less, fairly enough. Elements that are equal to the pivot should be put in equal, and elements that are greater than the pivot should be put into greater. Then we recursively divide the sub-arrays into lesser and greater until only one element is left. Then you can concatenate the arrays back together, starting with less than, equal than, greater, and you end up with sorted data. Now we'll see that in practice. So here we've got an array of, how many is in this one? 1, 2, 3, 9 elements. Okay. And we choose something to be our partition element. So in this case, I've chosen 33, which is the last element in the array. It's something sometimes people do. Sometimes people use the first one, and we'll talk a little bit more about choosing pivots in a second. So I've chosen 33 at this point. I then look through my array and say what data is less than 33, and that goes on the left-hand side. So in this case, it's only 12 and 23. I then look at my data and say, is there anything equal to 33? There's not in this case. There's no repeat data in this case, so that's fine. And then I do the right partition. So I go into what's greater than 33, and that's 43, 55, 44, 64, 77, and 75. Okay. At this point, I can pretty much ignore that 33. I never have to touch that again. I now know that it's in the correct place. It's the only thing I do know, but I know it's in the correct place. So I then look at my two little arrays I've created on the either side of that pivot, the less than numbered one and the greater number one. So my less than number one, I've only got 12 and 23. Say I choose 23 as the pivot, and that's something I could do because I'm using the greatest number as the pivot. Then I will note that 12 is less than that and put that to the left. Okay. I've got more work to do in the greater than 33 side of my array, so it's from 43 onwards. What I do there is I'm going to choose a pivot 75 to begin with, which was at the end. So that leaves me with 77 just by itself on the right there. The lesser numbers are 43, 55, 44, and 64. So that's quite good. And then I end up taking 64 as my pivot. Actually, everything's less than that, so it doesn't really help me very much. I then choose 44, and that splits me up with 43, 44, 45. So now what I can do is just concatenate this data back together. And if you look at the yellow numbers, you can see that these are where our pivots were. So we end up with the data sorted in exactly the correct order. Okay. This one does take a bit of practice. If you actually do it with the playing cards, remember just to shuffle them up. Choose a pivot at random. Maybe you can use the last element, which is what I've done here, and then go from there, and you'll actually see it coming out as you go. Okay. So the running time of Quicksort hugely depends on the pivot selection. Okay. Ideally, what we want to select is a pivot element, so the numbers of elements on the sub-left array, less than the pivot, are roughly equal to the number of elements in the right sub-array. So we want to be kind of dividing it equally each time right down. That allows for a really quick, efficient implementation, which is actually n log n times, the same as our merge sort earlier. The worst case scenario, though, is actually big O n squared. So actually, in the very worst case of Quicksort, and I'm going to leave it as an exercise for you to work out what that is, it's just as bad as insertion sort and selection sort. If we select a pivot from only the beginning or the end of the array, this actually can cause the Quicksort algorithm to run really slowly, especially in the case where the array is sorted or nearly sorted. And if we go back to my example right in the very first video, when I was talking about the timestamps of student applications coming in, and the fact we need to order by time, the chances are that that's actually fairly sorted data. And that's not that unusual a scenario. You usually have to sort just to be absolutely sure, but actually what you're dealing with is reasonably well sorted. So, as stated in the previous page, the efficiency of the Quicksort algorithm depends on the pivot selection. To improve the chance of selecting the right pivot, we may want to introduce some randomization. So we might want to take a pivot at random rather than at the beginning or the end of the array, and that is often referred to as a randomized Quicksort. Another pivot selection heuristic, and remember, heuristics are only rules of thumb. They work some of the times, they don't work the rest of the time, is called the median of 3. In this case, we take 3 values from an array, the first, the middle, and the last, and then we compute the median of 3. In larger arrays, we might actually take more than 3 values. And we take that median and we use that as the pivot. There's quite a few sort of heuristics or ways that you can choose a good pivot. And actually, it's a really important thing to do, because the better the pivot, the better the behaviour you get, and you get the closer to that perfect big O n log n complexity. Okay. So that was Quicksort. You'll be glad to know that I think in many ways it's the most complex of the algorithms we're discussing today. So I'll be back to you in a minute with bucket sort.